Welcome back. We are going to, without much further ado, jump straight into power series and Taylor series. I started this last time, and I want to sort of pick up from where I left off by reminding you of the two main things that we talked about last time, and now I'm going to add a third thing to this list. So the first thing that I had written up was something like this. E to the x is approximately equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial. I said this is true when x is near 0. When x equals 0, then both sides equal 1, and it's not even an approximation, it's perfect. But when x is a small number, positive or negative, but something close to 0, then this is an approximation. And in particular, we had substituted in x equals minus a tenth, and we found that e to the minus a tenth was approximately equal to, I think, 5429 over 6,000, which was easy enough to calculate just by plugging a tenth into that. And the beauty of it is we don't need a calculator or anything like that. Now, this, of course, is a very special case of the more general Taylor approximation theorem, which I wrote up last time, which basically said that f of x is approximately equal to Pn of x when x is near a. So instead of just dealing with e to the x and 0, I'm dealing with some other function f and some other point a. So a could be 0, as it is in this case, or it could be some other number, and f of x can be any smooth function, e to the x in that particular case. Pn is the nth order Taylor polynomial, and you need to know the formula for it. Well, let's say nth order Taylor polynomial about x equals a. I didn't actually explicitly write a here. I'm just assuming that for any individual problem that you or I work on, we're going to pick a at the beginning and fix it. And I don't want to bother around writing in the value of a every time. But the definition of Pn in sigma notation is it's the little nth derivative evaluated at a divided by the quantity n factorial and then times x minus a to the n. And you sum that over all the powers or all the values of little n from 0 to big N. It's very useful to know that in sigma notation, and it's also very useful to be able to write this out. It turns out to be the first few terms look a little bit different. I'll write out one more term at the beginning, the third derivative, 3 factorial. And this goes on up until the capital nth derivative, the capital N factorial, x minus a to the capital N. Okay, so this was the first main concept, that you can use a polynomial to approximate a function which is not a polynomial. Actually, it turns out that if, for example, f happens to be a polynomial of degree capital N or less, then this is equal to the polynomial. So if you try to approximate, say, a degree 4 polynomial by a degree 4 or 5 or higher order Taylor polynomial, you will just get the original polynomial back. There is no better polynomial that approximates a particular polynomial than the polynomial itself. On the other hand, if you do start off with, say, a quadratic, well, not a quadratic, let's say a degree 5 polynomial for f, and you use a lower number like P3 or P4, then you actually will get an approximation. So you can approximate degree 5s by lower degrees. Anyway, so the first concept, as I said, is approximation. The second concept extends this. Oh, by the way, in this example here, I stopped at 3. That's capital N equals 3. But of course, I could have kept going. Or I could have stopped at 2. I get different levels of approximation. So the next concept is I had written actually that e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And instead of writing an approximation, I'd written e to the c over 4 factorial times x to the 4th. And that's true for some number c between 0 and x. So in particular, when x equals minus a tenth, we had said that e to the minus a tenth actually equals 5429 over 6,000 plus e to the c, and it turns out this expression was 240,000. I did this last time right at the end of the class. So this is true, and all we know about c is that it's between minus a tenth and 0, because x is minus a tenth. So this is really nice. This extends the first concept from above by telling us how good the approximation is. I say this approximately equals this. How good is it? To tell, what you have to do is look at the deficit, or what you have to add or subtract to the approximation to get the true value. And again, this is a special case of Taylor's theorem, which said that under the correct conditions on f, it actually equals the polynomial, not approximate, but it actually equals the polynomial plus a remainder term, which we write Rn of x. And Rn is given by, and this is the real content of the theorem, it's the n plus 1th derivative over n plus 1 factorial times x minus a to the n plus 1. And if you just plugged in an a there, you'd get the next term of the Pn. It would be actually the Pn plus 1, the highest degree term of this. But it's not at a. It's at some number c, where c is in between x and a. So you pin it down somewhat. The closer x is to a, the more control you have over c. In this case, x is minus a tenth, and a is 0. So c is trapped between this fairly narrow range, or in this fairly narrow range, between minus a tenth and 0. So that's the next sort of concept. We improve the approximation. Now, I'm going to move on to something new for this week. And this is sort of the third concept of the 3. And in my book, it's actually, I've sort of moved on to section 24.2. So now what I want to do is look at this. I stopped at 3, so the remainder was 4, of degree 4, and that's it. Of course, I could have done the original approximation up to 100, and then the remainder would be 101. The more I do it, the better the approximations and the smaller the remainder. I say remainder, this Rn is called error term or remainder term. As I said last week, the R is for remainder. So the logical extension is that you'd like to be able to write this. E to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on. Infinite series. So that's a different sort of flavor. But unlike, well, in 1 above there at the top of the board, it's only an approximation. 2, it's perfect. It equals, but we don't know what c is. We just have it trapped in some range. And 3, everything, it's equal, and there's no uncertainty, but there's an infinite series. So you cannot fit a round peg into a square hole, or whatever the expression is. There's got to be some sacrifice when you use a polynomial to deal with something that is not a polynomial. And it's got to be somewhere, either an approximation or an unknown number c, or, in this case, an infinite series. Now, this is a true statement for any x. What does it mean? Let's put in x equals minus a tenth again to get an equation. It says e to the minus a tenth is 1 plus minus a tenth plus minus a tenth squared over 2 factorial plus minus a tenth cubed over 3 factorial, and so on. And another way of writing this, well, let's actually just tidy it up. It becomes alternating. 1 minus a tenth plus 1 over 10 squared 2 factorial minus 1 over 10 cubed 3 factorial, and so on. So it's alternating, as it turns out, and the powers of 10 march upwards and the factorials march upwards, and you get the pattern. Now, what does this equation mean? What it means is the right-hand side is an infinite series of the sort that we've been discussing for the last few weeks, and it converges. Not only do we know it converges, we know it converges to e to the minus a tenth. So another way of, the way I want you to think about this is an infinite series which converges, first of all, converges to e to the minus a tenth. So I kind of want you to think of it as, hey, it's an infinite series, it converges, and what's more, we know what it converges to, e to the minus a tenth. And the beautiful thing about the above expression, the e to the x one, is that for every value of x you plug in, and there's infinitely many to choose from, pick any number, real, negative, positive, any number you want, plug it in to both sides, and you'll get on the right-hand side an infinite series which converges, and the limit of that is the value it converges to is e to the whatever you plugged in. So this is like infinitely many series that you have the convergence, and you know what it converges to, 1 for each x. And that's pretty nice. That's pretty nice. That's a powerful equation. You get infinitely many series for free. Of course, they're all very similar. They're all in the same mold or template. Okay, so this is more an expression of power series. The first was Taylor approximation. The second is Taylor's theorem and Taylor series. And this is more along the lines of the power series idea. So what I wanted to do is give you a brief overview of what we're going to talk about in the problems. Now, what I want to do is I want to look at one aspect of this. In fact, I want to prove this from the second result and sort of show you how actually this is really an evolution from 1 to 2 to 3, and they all sort of follow from each other. But then I'm going to drop the power series and go back to 1 and 2 and do a whole lot of problems involving approximations and estimations. Then, in whatever time is left over, I'm going to show you how to do a whole lot of problems about power series. So that's the plan of attack. This is the overview of the whole idea in a very brief nutshell. So, soon I want to attack problems, but, it's conceivable in Math 104. Pretty unlikely, but it's vaguely conceivable to me that you may be asked to show that the equation, or an equation like this, the one I just wrote up, is true. For all x. How would you prove such a thing? Using the Taylor theorem. That's the question. Okay, as I say, I don't really think this is very likely. It's more for a quiz. If you're watching online, maybe at your college, this might be fair game. But in any case, I think it's important that you see it, even if you don't ever have to do it. So I'm going to show it to you. So I'm assuming that we have this theorem, the Taylor theorem, that f of x is Pn of x plus Rn of x. Now, what are the three things we can choose? Well, there's always three things that are involved. One is the function f. And by the way, this is going to come up over and over again. So you always have a choice of f of x, you have a choice of a, and you have a choice of n. Once you've picked those three things, the formulas tell you how to proceed. So in our case, we'll pick f of x being e to the x, and we're going to pick a to be 0. And n, I'm not going to say yet. I'm not going to pick a specific value of n. I'm going to leave it open. Now, so what is Pn of x? Well, by the formula that I wrote on the previous board there, it looks like f of a plus f prime of a times x minus a plus f double prime of a. This is a very useful formula. And so on until we get up to the nth derivative at a. And don't forget to divide by the factorials. Okay, that's true in general. Let's specialize first using a equals 0. So for a equals 0, this is f of 0 plus f prime of 0 x plus f double prime of 0 times, I left out the squared up here. And I left out the n here. Okay, please fix that up. Maybe we can pan the video over there. I was writing in a hurry. Need that nth power there. So all I've done is replace every instance of the variable a, with the number 0. Now, what we're going to need to know all the derivatives of f. And luckily, e to the x is a very, very simple function. What I'm going to do is set up a little table that looks like this. I'm going to write n here. I'm going to put the nth derivative of f in general, and then the nth derivative at the special point a, which happens to be 0. And let's just do 0, 1, 2, 3 to get the idea. So the function itself is e to the x. Remember, the function is the 0th derivative. It's the same thing. 0th derivative, take no derivatives. You just get your function. However, the first derivative is e to the x. The second derivative is e to the x. The third derivative is e to the x. Hey, every derivative is e to the x. Now we plug in 0, and we get 1, 1, 1, 1. All the derivatives are 1 when evaluated at 0. And now you can just use this table to plug in these ones, these numbers for f of 0, f prime of 0, f double prime of 0. You just read down the column, which in this case is not very exciting because they're all 1. So you get 1 plus 1x plus 1x squared over 2 factorial up until 1x to the n over n factorial. Okay, so that's the Pn of x. We shouldn't be surprised. This is the formula that we've been seeing. Now, how about Rn of x? Well, again, this is sort of repeating what we've done. We just need the formula. In general, it's the n plus 1th derivative at c, n plus 1 factorial, times x minus a to the n plus 1. And what do we know? We know c is between x and a. So that's the general formula. Let's now first specialize to a equals 0. And so we get, again, the nth derivative at c of n plus 1 factorial times x to the n plus 1. And c is between x and 0. And finally, we know all the derivatives of e to the x are e to the x. So this is e to the c. Okay, so since f of x is p of n, Pn plus Rn, we can write well, in fact, we already wrote that before. Now, here's what I want to do. I want to take the limit as capital N goes to infinity of Rn of x. I want to look at this. Limit as capital N goes to infinity of Rn of x. What happens when we take more and more powers in our Pn and push it forward? What do we think happens to the error? So the more degrees we use to approximate e to the x, what happens to our error? Hopefully it goes down to 0. Let's prove it. This is the limit. Actually, I'll take the absolute value just to be a little bit snazzier about it. Doesn't make a difference since this is going to be 0. So we've got to see what happens to e to the c over n plus 1 factorial absolute value of x to the n plus 1. I just took absolute values. E to the c is always positive. N plus 1 factorial is positive. So the absolute values can just go around the x. Now, what do we think this is? Now, first of all, note that it's the limit as n goes to infinity. It has nothing to do with x or c, just the n. Okay? So here's a question. How big could e to the c possibly be? C is between 0 and x. So how big could it be? Well, it could be as big as e to the x if x is, say, 2. Suppose x is 2. C would be between 0 and 2, and e to the c would be between e to the 0 and e squared. So it could be as big as e to the x. But x is a constant. So the point is that actually e to the c is sort of, there's not a lot it can do. It's between 0, certainly, because exponentials are always positive, and some other constant, big C. And it doesn't really matter what this is. Now we're going to use the sandwich principle. What I want to know is, what is the limit of, let's replace absolute value of x by r so that we're not confused about anything like this. What do you think this limit is? Well, it's an exponential on the top, but it's a factorial on the bottom. And it turns out factorials grow much faster than exponentials. Now that's an interesting fact that deserves a proof. I am not going to spend time on the proof. Instead, I encourage you to look at the end of chapter 24 for this proof, to show that the exponentials, although they grow really, really fast, think of this as like 2 to the n, or 2 to the n plus 1. Exponentials grow fast, but factorials are really, really fast. Faster than exponentials. They crush them. So that limit is 0. And so basically, we can use the sandwich principle. This is less than capital C times r to the n plus 1 over n plus 1 factorial, where I've let r be equal to the absolute value of x. And so, again, it is described at the end of chapter 24 in some more detail, but basically we can see that this limit must equal 0 by using the sandwich principle. Basically, the top grows exponentially. This is just not a trouble. This is the exponential, but the factorial on the bottom kills everything and pushes it down to 0. So having said that, we can take a limit here. Since it's true for every n, it's also true in the limit. But we've just decided that the error, the Rn, goes down to 0. So it's the limit as n goes to infinity of the Pn. Now, what is Pn? Well, we just worked it out above. It's x to the n over n factorial. And maybe I should amend this over here. Maybe we can just come back up here. I should have written this in sigma notation for simplicity. It's easy to see that it's x to the n over n factorial. That's just the sigma notation version. Okay, so having got that, let's come down here again. So what we've said is, we do it at some capital N. The larger this is, the smaller this is. The larger capital N is, the smaller the remainder. And in the limit, it goes away. So f of x, which is actually equal to e to the x, is the limit that's shown there. And that's true for any x. And of course, this is the same thing as the limit of the partial sums, which is the infinite series. So I've left out a few details, and you have to check the end of 24 for them. But basically, the idea is there. The bigger the polynomial, or the bigger the degree of the approximating polynomial, the better the approximation. And as you push that degree up, the approximation becomes closer and closer to perfect. In the limit, it is perfect. Any questions about that? It's a little theoretical, I admit, but it's sort of important. It's just one example, but that's like a key example there. Any questions about it? If you have one, just shout it out. Okay, so from here, this is the general formula for Rn. Okay, there's actually nothing on the top board that tells you anything about it. Rn is this, always. Okay, it's just a question of specializing to your choice of f, n, and a. Okay, f, well, I did a equals 0 first, which I had just chosen. Right? I mean, we could have chosen a different number. You get a different series for Pn. There's a different series for each a that you choose. But in any case, so a is 0, so that reduces it to this. And then f is e to the x, which reduces it to this. And notice that c is between x and 0. I specialized that a as well. But I never specialized the capital N. Instead, I let the capital N go to infinity, and this term goes to 0. That's the whole sort of gist of it. Leaving only this approximation here for better and better approximations which converge to the actual value that you want. Anyway, so if that seems a little mysterious, take heart, because, as I said, at least in Math 104, these things don't really come up very much. However, I am going to now move on to chapter 25, which is how to solve problems involving approximations. Okay? So this is in a slightly different order from the way you've covered it in class, but this is kind of the way I think I like it anyway. So, check out first 25.1. That contains a summary of everything that I've said about Taylor series, plus a few other little facts I said last week. Let me just remind you, when a equals 0, as it did in the previous case, it's called a Maclaurin series. So just one little thing, Maclaurin series, it's just Taylor series, Taylor polynomials, Taylor series with a equals 0. By the way, I've said what a Taylor polynomial is. I didn't really say exactly what a Taylor series is. I don't want to get bogged down in the details, but Taylor series is just when you go to infinity instead of stopping it at some value. So, Taylor series, Taylor polynomial, very similar. Maclaurin means a equals 0. I actually do not know really the history of why a special case of Taylor is named after Lord Maclaurin. I don't know, maybe Taylor did it first and then Maclaurin came along and said, let's set a equals 0. But probably it was the other way around. I don't know. Anyway, when you say Maclaurin, thing in your brain should be, oh wait, that's just Taylor, but a equals 0. Anyway, so I urge you to look at this for this summary, but instead I want to talk about 25.2, where I'm going to say, okay, how would you find, here's just some examples. So let's find the Taylor series of e to the x, once again, about x equals, did I say 2 or minus 2? Let's do minus 2. Okay, we already found, actually, the Taylor series of e to the x about x equals 0. That was the previous example. But now it's a different question. It's now x equals minus 2. So we proceed in a similar sort of way. I'm going to set up a table. All of these problems we need to set up a table. It always looks like this. N, the nth derivative in general, and the nth derivative at our special value. Now what is our special value? Minus 2. This is a. So instead of writing in a, I will immediately specialize to minus 2. All right, and then it's not quite clear how far down you have to go. I always think you should leave more space just in case you have to add more rows to this table. But in any case, here we have copy down the function e to the x. We're going to call this f of x once again. And so the derivatives are just e to the x. So this isn't particularly exciting. You plug in e to the minus 2, e to the minus 2, of course. So I've plugged in minus 2 to get e to the minus 2, I should say, and so on. So the Taylor series, I don't really have a name for it. Maybe I'll call it p of x, is f of a plus f prime of a, x minus a, plus f double prime of a over 2 factorial, x minus a squared, plus the third derivative. You get used to writing this out, I tell you. And because it's the Taylor series, it never stops. I don't know how far out to go. I'm just going out to 3. But in this case, a happens to be minus 2. So I'm going to immediately specialize to a as minus 2. And at the same time, I'm going to copy the values of f of minus 2, f prime of minus 2, f double prime of minus 2, f triple prime, etc., from this column here. And once again, they're all equal. So it's e to the minus 2 plus e to the minus 2. X minus minus 2 is actually plus 2. Plus e to the minus 2 over 2 factorial. X plus 2 all squared. Plus e to the minus 2 over 3 factorial. X plus 2 all cubed. And so on. And that's the Taylor series. If you want, you can get fancy and write it as a sum. E to the minus 2 over n factorial, x plus 2 to the n, and it never stops. Okay, so that's the complete Taylor series of e to the x about x equals minus 2. It's quite similar to the series about 0, but not quite the same. Instead of x to the n over n factorial, we have x plus 2 to the n, and we also have this extra factor of e to the minus 2 in every term. So you see, the Taylor series for e to the x, no such thing. Taylor series of e to the x, where? Minus 2, 7, 0, a million. You get a different Taylor series for each center. I should say that a is often called the center of the series. Now, another type of question, similar, might have been, give the first, say, 4 terms of the Taylor series. Well, 1, 2, 3, 4. You just stop there. If it was only the first 3 terms that we wanted, just give those. On the other hand, if the question said, give the first 5 terms, you'd have to write out one more. If it just find the Taylor series, it's up to you to put the dots or the infinity. I mean, you've got to be sensible about the dots. You don't want to write e to the minus 2 plus dot, 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 because then we can't work out what the hell the pattern is. You have to have enough to see what the pattern is there. Now, on the other hand, what if the thing said, give the terms up to 4th order? Well, this is the first 0th, first, 2nd order, 3rd order. We'd need another term. I'm just trying to give you a flavor of what we're achieving here. We know what the answer is. We've written it down. Everything is great, but just be aware there's some slight permutations of the problem. Maybe we'll see some of these In fact, let's suppose I ask for the Taylor series. So here's another example. I want Taylor series for sine x about x equals pi over 6 up to fourth order. Remember, order is the same as degree, except that the fourth order term might be 0. If the derivative happens to be 0, perhaps the fourth order term is 0, which would actually lead to a degree 3, or even 2, or 1. So the fourth order means you write down the template up to x to the fourth, but don't worry if the term becomes 0. So order is bigger than or equal to degree. Okay, so let's solve this problem. Same sort of tactic. Set up the table. N, nth derivative in general, and the nth derivative this time at pi over 6, because that is going to be our a. And this time f is sine x. Okay, well we need the terms up to fourth order, so I better go up to 4. Okay, so what is the function itself? Well, this time it's sine x. And now I differentiate it over and over again. So the derivative of sine is cosine. Derivative of cosine is negative sine. Then negative cosine. And then finally, I'm actually back to sine. I'm not going to keep going because I only need up to fourth order. But in principle, if I kept going, I'd just repeat this pattern. Now I plug in sine. I plug in pi over 6. And you have to remember, what is sine pi over 6? It is sine pi over 6. 1/2. Okay. It's really helpful to have those, of course, at the tip of your fingers. How about cosine pi over 6? Root 3 over 2, and then negative 1/2, negative root 3 over 2, and then 1/2 again. So what we're actually asking for is P4 of x in this case. And in general, it looks like f of a plus f prime a, x minus a, plus f double prime over 2 factorial, x minus a all squared, plus the third derivative over 3 factorial, x minus a all cubed, plus finally the fourth derivative over 4 factorial, x minus a to the fourth. That's the fourth order Taylor polynomial in general. See how useful it is to be able to write this? Now I'm going to immediately just plug in these values, which are now not all the same, in place of these derivatives here at a. And I'm also going to put a equals pi over 6, just to remind myself of this. So in this case, I get 1/2 plus root 3 over 2 times x minus pi over 6, plus the second derivative is minus 1/2 over 2 factorial, x minus pi over 6 all squared, plus the third derivative is minus root 3 over 2 over 3 factorial, x minus pi over 6 all cubed, and finally the fourth derivative is 1/2 x minus pi over 6 all to the 4. So it's sort of plug and paste, but it's a much more complicated formula than just about any of these sort of things you've seen before. It's worth tidying this up a little bit. I get 1/2 root 3 over 2 x minus pi over 6. 2 factorial is 2, so I get 1/4 x minus pi over 6 all squared. 3 factorial is 6, so minus root 3 over 12 x minus pi over 6 all cubed. And finally, 4 factorial is 24. So this will be 1 over 48. X minus pi over 6 to the fourth. All right. It's easy when you have the table and you have the formula. Unfortunately, the question just says, find the Taylor polynomial. It doesn't tell you that you need to know the formula. It doesn't tell you what the table is. It doesn't tell you what f is or a or anything. It's extremely minimalistic. And yet, that's what you have to do. Any questions? All right. So there's another example which is quite interesting in the book. It's in section 25.2, but I don't think I have time to do it, so I urge you to read over it. Anyway, if there are no sort of questions about that, I'd like to now extend this to the real meat, the real problem here, which is estimation. So I'm going to spend quite a while on this. It's not unrelated to what I was just talking about, but it's more. Estimation problems. Okay, maybe I'll hold on to this for a second. So estimation, approximation, same thing as far as I'm concerned. You're trapped on a desert island without a calculator. For some reason, you cannot escape the island unless you tell someone what the value of e to the 1/3 is and how accurate it is. Okay, so before I was doing e to the minus a tenth, I just feel like changing it to a third for this example. So I'm going to kind of reiterate what we've done, but be a little more precise about it. Now, here are two flavors of this. First question. Estimate using Taylor poly of order 2 and estimate the error. And a similar but significantly more difficult problem is to estimate this with an error less than or equal to 1/10,000. So I want the value of e to the 1/3 accurate to 1/10,000. That's like 4 decimal places. All right. So these are very similar problems, but the second one is much more difficult. Now, there is a method for doing this, for these sorts of problems. So what I'd like to do is sort of talk you through the method and solve this problem at the same time. So, actually, let's do A first. I have some freedom. The book, it's hard to do two things at the same time in the book. But here I can take columns. So I think I have the freedom to just show you what's involved in A, because we've basically already done it. Look, we're going to do this. Set f of x equals e to the x. Remember, there's three things to pick. F, A, and n. A is going to be 0 because it's a number quite close to 1/3, and we know exactly what e to the 0 is. It's probably the closest number to 1/3 that we really know a lot about e to the power of. And then finally, we're going to take capital N equals 2, because the question says use a Taylor polynomial of order 2. So just quickly throwing up the same table that I actually just erased. Nth derivative in general, and the nth derivative at 0. I only need to go up to 2. All the derivatives are e to the x. So you get e to the 0 is 1, 1, 1. So basically, f of x is approximately equal to p2 of x. And p2, again, is f of a plus f prime a, x minus a, plus f double prime of a over 2 factorial x minus a all squared. And in this case, a is 0, this is 1, this is x squared over 2 factorial. And that's exactly what we've seen before. So in this particular case, this is e to the x. So we have our approximation. E to the x is approximately 1 plus x squared over 2. And put x equals a third. And you'll see that e to the third is approximately 1 plus a third plus a ninth over 2, which works out, I'm being very lazy here, to be 25 over 18. Okay, so e to the third is approximately 25 over 18. That tells us what the estimate is, but it does not tell us how big the error is. So to get the error, I'm going to look at R2 of x. I used P2, so of course I have to use R2. I do not have to use D2, though, because this is not Star Wars. So anyway, you couldn't hear it on the video, but there was actually a complete absence of reaction to that, so just in case you were wondering. Now, here I have C between x and a. That's the general formula. Again, the third derivative is e to the c, and it's going to be over 6, x cubed, because a equals 0. And c is between 0 and x. So now, what have we done? We have said e to the 1/3 is f of 1/3, which is p2 of 1/3 plus r2 of 1/3. p2 of a third we just found is 25 over 18. And r2 of a third is e to the c times a third cubed over 6. And what do we know about c? It's between 0 and a third. So this is probably déjà vu from last week because we did a very similar example. So you get e to the c, and 6/27 work out to be 162. Is that right? 168. No, it is 162. There you go. All right. So this has improved the previous thing because we now know that e to the third is this, our original approximation, plus e to the c over 162. The problem is we need to estimate this quantity without even knowing what c is. In fact, we need to overestimate this quantity. We'd rather be more conservative about the error. So my question is, how big could this possibly be? How small could it possibly be? Anyone want to contemplate this? It's smaller. It's actually at least 1 over 162 because e to the 0 is 1. That's the lowest part. But how big could it be? That's what we really care about. How big could it be? E to the 1/3. So error, let's work over here. Error is e to the c over 162, and the biggest this could be is e to the 1/3 over 162, because e to the c is increasing in c, and c is at most a third. Problem is, we don't know what this is. What is e to the 1/3 over 162? Actually, isn't the whole problem to estimate e to the 1/3? Now the error also involves e to the 1/3. It's kind of frustrating. But on the other hand, we just need to estimate the error. We can be quite crude about it. We can overestimate how big it could possibly be, and it will still be a correct estimate. So I'm going to do the crudest estimate that I can to get a handle of how big e to the 1/3 is. What's e? 2.7. The third is the cube root. What's a number bigger than e that you can take the cube root of? It's not too much bigger, but what's the smallest easy to take a cube root of number bigger than e? 8. So I'm just going to do something and say this is certainly less than 8 to the 1/3 over 162. And 8 to the 1/3 is 2, so this is 1 over 81. So that's my estimate for the error. So in conclusion, e to the 1/3 is equal to plus an error of less than 1 over 81. That's about how accurate it is. Maybe it's a little bit better than that, but there you go. And actually also this is an underestimate because the error term is positive in this case. E to the c over 162, exponentials are positive. Bless you. Right. So that is part A of the problem. Now, does this also work for part B, which is to estimate it to at least, at most, rather, 1 over 10,000 error? No, it's no good. 1 over 81 is a small number. We've sort of nailed it, but we'd like to tighten it up to a closer thing. So the difficulty is this. I spoon-fed you in part A the value of n. Capital N is 2. It said in the problem, use a Taylor series of order 2. The real issue is, how do you know what capital N is? How do you know what it is if you're not given it? In the second problem, where you have to estimate to 1 over 10,000, you need to find out what n is first before you start writing down the polynomial and thereby the approximation, because you don't know how far you need to go. So I say, instead of starting with the Pn, we'll start with the Rn. And then we're going to try to find out what n is. So for part B, start with Rn of x. So again, we still have Rn of x, nth derivative at c over n plus 1 factorial times x minus a to the n plus 1. And we still know that f of x is e to the x. And we still have a as 0. And eventually we're going to put x as 1/3 because we want e to the 1/3 power. So the problem is we don't know what n should be. So let's specialize this. In general, we have Rn of x is e to the c, because all the derivatives are e to the x. Evaluated at c, you get e to the c, over n plus 1 factorial, x to the n plus 1, again, c between 0 and x. Same as what we wrote before, but I don't know what n is. Now, we're interested, let's just remind ourselves what we're doing here. We are writing f of x is Pn of x, which is the Taylor polynomial, plus Rn of x, which is this error term. And f of x is just e to the x. So maybe I'll write this like this. And then we're going to put x equals 1/3. And we're going to get e to the 1/3 is Pn of 1/3 plus Rn of 1/3. This is the approximation, and this is the error. Okay, so actually, since the error is Rn of 1/3, we need to put x equals 1/3 up here, and you get Rn of 1/3 is e to the c over capital N plus 1 factorial times 1/3 to the n plus 1, and we know that c is between 0 and 1/3. You don't need to write that as part of the solution. This is just for our edification. Anyway, so here we are. What is n? We don't know. But we need to choose it so that this quantity is no more than 1 over 10,000. So we need this error in absolute value less than or equal to 1 over 10,000. That's what the problem asks for. Find e to the 1/3 accurate to it at least, so an error no more than 1 over 10,000. So basically, I need, since everything is positive in this case, i.e. we need to find n so that e to the c over n plus 1 factorial times 1 over 3 to the n is less than 1 over 10,000. Luckily, everything's positive, so we can drop the absolute values, as I said. And the extra complication is we don't know what c is. We just know that it's between 0 and 1/3. Question? Oh, I left out that plus 1, didn't I? Okay, thank you. Good. So, I need to find the n so that that is true no matter what c is, as long as it's between 0 and 1/3. Well, I don't know what it should be. You kind of just have to do a little scramble around. But one thing you should notice is that we should pick the worst possible value of c. In fact, we know, again, that the biggest it could be is 1/3. And again, I'll do my trick of saying that this is less than or equal to 8 to the 1/3, because we can play around as long as we don't make things smaller. We can make things bigger, which of course equals 2 over n plus 1 factorial times 3 to the n plus 1. And the main advantage is I've gotten rid of the c. So I want this to be less than 1 over 10,000 again. Okay, so notice how I passed from this equation, which was the actual equation, to this, or this inequality, I should say, to this inequality down here, which doesn't have a little c in it. By just assuming that everything is as bad as possible, how big could the c thing be? Well, it's certainly less than or equal to 2, which is good. Now, I just have to pick an n large enough. Now, I don't have an easy formula for this. All I can suggest is, we know n equals 2 doesn't work. Let's just try n equals 3. You get 2 over 4 factorial times 3 to the 4. Well, 4 factorial is 24. 3 to the 4 is 81. That's not going to be good enough. That's not going to give us 1 over 10,000. Let's try n equals 4. You get 2 over 5 factorial times 3 to the 5. Okay. 5 factorial is 120. 3 to the 5 is actually 243. So this is 1 over 60 times 243. Well, 6 times... Well, let's just work it out. I don't have a calculator, so... We don't even need to be so precise, but I just want to get an idea. So it's 14,580. I think that's right. So, is that good enough? Yes, that is less than or equal to 1 over 10,000. So n equals 4 will do. Now, you might say, well, what about n equals 5, 6, 7? Yes, they are all even better. So any number that is 4 or bigger will work. You do not have to pick the least one. It's not necessary. No one is asking for what is the stingiest approximation you can make. You can always make a better one as long as it's within 1 over 10,000. However, you cannot make a worse one. So you need to take at least 4. Okay, there's no prizes for getting the first value of n that definitively works. There's no need to do it. On the other hand, the more n is, the more terms you have to write out in the approximation. Watch. We have now determined that the error is less than or equal to 1 over 10,000 when n equals 4. So I can now say e to the x, or e to the 1/3, is approximately equal to p4 of 1/3. And I need to use, therefore, a Taylor polynomial of a third, which is, well, let's just write down in general, P4 of x, no doubt looks like this. We don't need to reinvent the wheel here. So when I plug in a third into this, I get 1 plus a third all squared over 2 factorial plus a third all cubed over 3 factorial plus a third to the fourth over 4 factorial. And you can work this out, and I did once upon a time. It's not that bad. What does it work out to be? It works out to be 2713, 1944. But that might be a little bit too much to expect you to do in a final. So this I sort of did the other way around. When I did part A, I worked out the approximation first, and then I worried about the error. But for part B, I could not do the approximation until I knew what n to pick. And to do that, I had to deal with the error first. So I've completed the problem. The approximation is this, and the error is at most 1 over 14,580, which is good enough. Certainly less than or equal to 1 over 10,000. Okay, so actually, I have decided not to write out the complete method. If you are interested, it is in the beginning of 25.3 as a 9-step method. But honestly, you will pick it up as I do some more of these problems. So I have to do some more examples. I have 5 examples in section 25.3 and its subsections. I'm not going to do all 5 of them because it would take too long. But instead, I really recommend that you read through them and try to work along them. Don't just read it. See if you can read the question and then generate the solution and use this to check your solution. Because these are probably the hardest problems in the whole course. Or at least they're right up there with the hardest in Math 104. They always are problematic in terms of when we grade the finals, these types of approximation problems have very low success rates. So if you can master them, you will be in very good shape. Okay. So let's do this problem. Estimate 1 over root 23. With an error less than or equal to 1 over 250. Okay. That's the problem. Doesn't mention Taylor, doesn't mention anything. Still, you know estimation and approximation problems are going to involve Taylor series. And you know with Taylor series, there's 3 things you need to pick. You need to pick your f of x, you need to pick your a, and you need to pick your n. And actually, eventually, we're going to substitute for x as well. Well, no one is going to tell you what f should be. You need to pick it yourself. And this is actually where a number of students historically have seemed to have gotten stymied because there was no function. What is f of x? Root 23? No, you have to ask, what are you really doing to the 23? You're taking the square root of it. So you have to let f of x be equal to root x, which I'm going to write, well, let's just write it as root x. I could write it as x to, what the hell, x to, that's easier to differentiate repeatedly. Okay, a should be a number close to the 23 that we can easily take the square root of. Any candidates? 25. Again, you have to pick that yourself. Unfortunately, we are not given n, and that will be our first task. And eventually, we're going to need x equals 23 in the end. But save the x for the very end. It's much better that way. Okay, so let's follow the procedure. Let's tackle the error first. Rn of x, in general, is equal to the nth derivative at c, n plus 1th derivative, rather, at c of n plus 1 factorial, x minus a to the n plus 1, and you must write c between x and a. Well, we're going to need a table, so I'll throw it in here. This is going to be n, the nth derivative in general, and the nth derivative at 25. That's what we care about. So I don't know how many of these rows I'm going to need. I'll go up to 3, say. The function itself is x to the 1/2. We need to differentiate this a few times. The first derivative is 1/2 x to the minus 1/2. The next derivative is minus 1/4 x to the minus 3/2. And finally, 3/8 x to the minus 5/2. I say finally, I'm just being optimistic here. I might need to keep on going. So that's why I can move the blackboard up. Who knows? Luckily, the error is not so big. It's only 1 over 250. If they wanted it to 1 over 250 million, I probably would have to go much further. Anyway, let's plug in 25. You get the square root of 25 is 5. You get here 1/2 times 1 over 5, which is, give myself a little more room, equals 1/10. Here I get minus 1/4 times 1 over 5 cubed. 5 cubed is 125. Right? 25 to the minus 3/2, by the way, is 1 over 5 cubed. So this is minus 1 over 600. And gee, this is starting to get hairy here. This is 3/8 times 1 over 5 to the 5. I don't even know what that is, so I'll just leave it. 17. Wow, whatever. Okay, so in this case, I don't know what it is. I don't know what n is. So the best I can do is write that this is f n plus 1 at c, and keep the n plus 1 factorial, and let's write x minus 25 to the n plus 1. Okay, so notice before I wrote e to the c for the previous problem because I had an easy formula for any derivative of f. Here, all the derivatives have slightly different forms. So I can't even really fill this in. But what I can do is substitute in x equals 23, which is what we want. So we have Rn of 23 is, again, the n plus 1th derivative at c over n plus 1 factorial times 23 minus 25 to the n plus 1. And again, c is between x and a. So here, c is between x, which is 23, and 25, which is a. This is x, and this is a. Okay, so the error that we're looking for, let's just simplify it a little bit, is this nth derivative, which we're going to have to grab from the table, at c over n plus 1 factorial times minus 2 to the n plus 1. Okay, so all I've done is taken the general formula and specialized it. I've specialized it to, I don't know what n is, but I've said a and x. I've plugged in. It's pretty feeble. That's all we've done. Now it's time to get serious. I want that error in absolute value to be less than 1 over 250. So we want the absolute value of Rn of 23 to be less than 1 over 250. Well, that doesn't really do us much. The absolute value minus 2 to the n plus 1, all that allows us to do is just drop the minus. So I have the absolute value of the derivative, n plus 1 factorial 2 to the n plus 1. Big whoop. Well, it's time to get our hands dirty. I feel lucky, punk. I'm going to try n equals 1. Try n equals 1. Try. So R1 of 23 in absolute value is the second derivative at c over 2 factorial times 2 squared. Well, now, the second derivative, look up in the table there. We don't want the second derivative at 25. Actually, we have no use for the right-hand column yet. We are interested in the middle column. The second derivative is minus a quarter c to the minus 3 halves. Absolute value of that. Over 2 factorial is 2, 2 squared is 2, so I'll just cancel this out down to a 2. And this is equal to 1/2 c to the minus 3 halves after you take the absolute value. And all we know about c is that it's between 23 and 25. Okay, I need to get rid of c. I need to work out how big could this possibly be. How big could that possibly be? Well, 25 to the minus 3 halves or 23 to the minus 3 halves. Is this function decreasing in c or increasing in c? When c gets bigger, does this get bigger or smaller? It gets smaller. So the biggest value is at 23 to the minus 3 halves. And who knows what that is? Who knows what that is, but I'll tell you one unfortunate fact. I don't think this is good enough. I don't think it's good enough because 25 to the minus 3 halves is equal to 1 over 5 cubed, which is 1 over 125. And we got a half of that, so you do get 150, but this is not smaller than it. This is too big. This is not less than 1 over 250. If it were 25, it would be fine. Actually, in the book, I do the example where instead of 23, you have 27. And very little is different. I actually do the 27 example first, before I do the 23. If you look in the book and you see the 27 example, it's also a 2 here because 27 minus 25 is 2. But the beautiful thing is, here c is between 25 and 27. And there, you can make this work. But unfortunately, when you have to go below 25, the error gets a little bit too big. So, I'm afraid this is no good. We're going to have to try n equals 2 instead. So, R2 of 23 is the absolute value of the third derivative over 3 factorial times 2 cubed, using the same formula. And the third derivative is 3/8. So what is this? This is 3/8 times c to the minus 5 halves divided by 6, because that's 3 factorial, times 8. Well, 8 and 8 cancel. 3 and 6 leave us with a 2. And we get c to the, let me write it out one more time. It's 1/2 c to the minus 5 halves. Okay, again, c is between 23 and 25. So how big could that be? The biggest it could be is 23 to the minus 5 halves. Now, we've got to get some feeling of how big that is. What is a number less than 23 that you can easily take the square root of? 16. So I don't know much about this, but I know it's less than or equal to 1/2 times 16 to the minus 5 halves, which is, the square root of 16 is 4. So that's 1 over 2 times 4 to the 5. And you don't need to know too much about that. 4 to the 5 is the same as 2 to the 10. So it happens to be 1024. So this is 1 over 2048. It's really not important what it is, as long as it's less than 1 over 250, which it is. So we have verified that when n equals 2, we're golden. Unfortunately, n equals 1 didn't work. Now, if you had tried n equals 2 first, then you wouldn't have wasted a little bit of time. So, there's no need to feel lucky. Again, there's no prizes for getting the smallest n. Anyway, we've almost finished the problem. The thing is, we don't have the approximation. We've only just gotten n. It's a lot of work just to get n, but there you go. That's how these things work. So let's finish the problem. What we've seen, just to reiterate, is that f of x is p2 of x plus r2 of x. Now p2, f of x is equal to, in this case, the square root of x. So this is p2 of x plus r2 of x in general. And when x is 23, we've seen root 23 is p2 of 23 plus r2 of 23. And we have shown that the remainder, r2 of 23, is actually less than 1 over 250. Actually, it was less than 1 over 2048, but who's counting? So 2 is the magic number that works for us. 3, 4, anything bigger than 2 would also have worked. But we're going to say that this is approximately, root 23 is approximately p2 of 23. How are we going to find p2? Write down the formula. p2 of x in general is equal to f of a plus f prime of a, x minus a, plus f double prime of a over 2 factorial, x minus a all squared. A is 25. Unfortunately, from the point of view of the camera, which was mysteriously sitting there for a second, the table is on the other side of the blackboard, and I kind of need those values there. So what I might do is, what the hell, I'll just rewrite the table. This is just a rewrite from the other side. 0, 1, 2 is all I need. I don't care what those values are, but just copying from the other side, I got 5 minus a tenth and 1 over 600. Is that right? Is that what it says up there? No, plus a tenth minus 1 over 600. Okay, so anyway, I'm just going to copy these three values. I get 5 plus 1/10 x minus 25 minus 1 over 600 times 2, factorial is 2, x minus 25 all squared. So root x is actually this is a good approximation for root x, any x near 25. But in my particular case, I want 23. So that's 5 plus a tenth times 23 minus 25 minus 1 over 1200 times 23 minus 25 all squared. And this, of course, is just 2 squared, which is 4. So it's easy enough to work this out. It's 5 plus 1/5 minus 1 over 300. And did I make a mistake? Minus 1, huh? Oh, yes, minus 1/5. 23 minus 25, thank you. And so that works out, I believe, at 1199 over 250. I find that a little bit hard to believe. I don't know. Maybe I'm hallucinating. I'm not so sure about the 1 over 600, but maybe that's what it is. I don't see a mistake. Oh, it's 500. It's 500. Look, come back over here for 1 second. 5 cubed is 125, and 4 times that is 500. Just a little arithmetic thing. So change that, and then that propagates over here. That was just a silly thing I did. So this becomes 500, this becomes 1,000, and this becomes 250 after all. Okay, great. So just a little hiccup. Sorry about that. All right, so there's the approximation. i.e., root 23 is approximately 1199 over 250, accurate to better than 1 over 250. Ta-da! Problem solved. Not so easy. Not so easy. By the way, you can't just say, oh, I'll pick n equals 10 and that's got to work. And just don't even justify it and say, oh yeah, well n equals 10 is always going to work. Well, okay, sure, n equals 10 is always going to work in Math 104 simply because we could not imagine being so sadistic as to make you compute anything higher. But nevertheless, it won't always work. I could say to you, oh, find an error less than 1 over a trillion, 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 and then probably n equals 10 won't work. So we could always thwart you by finding a really, really, really tiny error that we want. It doesn't matter. You still have to check it. You still have to do this work here that I've just done. All right. So are there any other questions about this? It's tough stuff. You've got to practice. There's, as I said, there's 5 examples. I've sort of done 3 of them, but there's a nice one of cosine pi over 3 minus 0.01. Try that. In general, I talk about some ideas of how to... You notice that you have to maximize this quantity involving c. And sometimes we've seen e to the c. Sometimes we saw c to the minus 5 halves in this example. If it's increasing, like e to the c, you just pick the highest value from the right endpoint. If it's decreasing, you pick it to the left endpoint, like we did in the previous example. Sometimes you get a sine or a cosine, right? You might have the derivatives involving sines. You might get a sine c in absolute value. Guess what you do with that? Less than or equal to 1, right? So you might have to play around to get this. You've got to get rid of the c. You have to always get rid of it by saying it's less than or equal to something bigger than it is. By the way, in this last example, we have an estimate here. Is it an overestimate or is it an underestimate? As in, is this bigger than the true value, root 23, or is it less than? How can you tell? You might have to look back at the right board to see what we did. Not so easy, huh? Think is bigger? Let's look at R2 of 23. We took absolute values, but before we took absolute values, we have the third derivative, which is 3/8 c to the minus 5 halves, divided by 3 factorial, and then actually we're going to have a minus 2 cubed. So in order to really nail it, you need to write down exactly what R2 of 23 is without absolute values. It is indeed 3/8 c to the minus 5 halves over 6, 3 factorial, times minus 2 cubed. So is that a positive quantity or a negative quantity? C to the minus 5 halves is positive. So this is negative because of the minus 2 there. So this is negative. If you look back over here, root 23 is our approximate value plus a negative quantity, i.e. minus something. So we have to take away from 1199 over 250 to get to our true value. So it's an overestimate. I've very rarely seen that asked, but it's possible. Question? We realize that by comparing a to x, as in, is this an overestimate because a happens to be less than, more than x in this case? And the answer is no. It depends on the sign of the derivative as well. And it also depends on the capital N. You see, in this power here, we have minus 2 cubed. But if this had been an even number, it would have been positive. On the other hand, the derivative would be negative. So actually, it always turns out in this particular example to be an overestimate, no matter which n you use, except maybe at the n equals 0 will still be an underestimate. But but basically, you cannot just guess. Its dependence on the sign of the derivative plus the power make it it's just unpredictable. It's just too many things going on. Okay, so you have to just check it directly. As I said, I have seen very rarely in Math 104 is it an overestimate or an underestimate, but yet knowing what you know, you have the power of being able to tell. Just don't take absolute values for that part, or else you will, of course, make everything positive. All right. So, as I say, please look over those other examples. Now, I have a bit to say about power series, but there's one other technique for estimating the error that I need to tell you about that does not involve this Rn formula, and therefore is much more pleasant, and we should be able to dispense with fairly quickly. Now, here's the deal. Suppose that you write down an approximation that is alternating, meaning that you write down something like P of 23 is 5 minus this, plus this, minus this, plus this. If you were to keep going, it was alternating. This is not a good example because it's minus, minus. So what I have in mind, though, is suppose that you have a situation where that's the case. And a particular example might be something like this. So estimate, and it's going to be an integral. The integral from 0 to 1, 1 minus cosine of t over t squared dt to within 1 over 3,000. Yuck. Looks horrible. Not as bad as you think, though. I'll try to explain. We need a function. Actually, before we even have a function, is this an improper integral? To add insult to injury? Kind of looks improper, right? Problem spot at 0. It's not so bad, though. We actually proved, using L'Hopital's rule, it's not hard to prove, that the limit as t goes to 0 of 1 minus cosine of t over t squared is 1/2. So if you graph this function, it doesn't actually blow up. It has a removable singularity at 1/2. So there's really no problem there. Kind of nice. Now, so it's not improper, not that you need that to solve the problem. We need a function. Here is a nice technique. Let the top endpoint be variable. Here is the function I'm going to use. The integral from 0 to x of 1 minus cosine t over t squared. Okay, I said no one is going to choose the function. What's the derivative of this function? Anyone tell me, just as an aside? Remember, to do Taylor series, you need derivatives, right? What's the derivative? Anyone tell me, just by looking at it? It's the derivative of the integral. Plug in the x. So it is 1 minus cosine x over x squared. That's the first fundamental theorem. Not so bad. So actually, we could take the derivative of f, and we could keep on taking derivatives. It gets a little bit messy, though, using the quotient rule and all that sort of stuff. Anyway, so the point is, though, that we have this function f. We need to know what happens at 1, but there is one thing nice, that f of 0, we know, is 0. Because the integral from 0 to 0 of anything is 0. So actually, we're going to pick a equals 0. So we'll let a is 0, we'll let f of x be this, and we want f of 1. Because f of 1 is the integral we're looking for. Now, I'm going to jump the gun just a little bit. Just a little bit. I'm going to give you a formula that's similar to the one for e to the x. And I'm going to tell you that cosine of x also has a series, and it looks like this. 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. So it's only the even powers, which makes sense since cosine is an even function. And it has this plus minus thing. So see how similar it is to the e to the x, but you just have the evens and you have minus plus minus plus alternation there. Okay, this is true for all x. Take this from me. By the way, the derivatives of cosine go cosine, minus cosine, and then sine, then cosine, and so on. So they repeat. And if you plug in 0, you get 1, 0, minus 1, 0, 1, 0, minus 1, 0. So this is just the formula, combined with a similar argument to the one I did near the beginning for e to the x. So when I say take it from me, you actually have the power and the tools to prove that formula, just the same as we did for e to the x. It's just slightly different. You use trig functions instead. All right, so rather than use the previous methodology to finish this problem, or even to start the problem, because I barely started it, let me instead set up this general sort of idea of how to use alternation to estimate the error. So I've sort of been dancing around the problem gingerly. I haven't really done anything yet. I've just sort of explored the complications. Now let's dig in. I'm going to start with my f of x. Now I'm going to do something a little snazzy. F of x is the integral from 0 to x, 1 minus cosine t over t squared, dt. I'm going to replace cosine t with this series over here. So I get 1 minus, the series is 1 minus t squared over 2 factorial plus t to the 4th over 4 factorial minus t to the 6th over 6 factorial, and so on, over quantity t squared. The 1's cancel out. So I get t squared over 2 factorial minus t to the 4th over 4 factorial plus t to the 6th over 6 factorial, and so on. You get the pattern. And then all that divided by t squared. And actually, this is nice. We can just take out a power of t squared from all of them, and I get 1 over 2 factorial minus t squared over 4 factorial plus t to the 4th over 6 factorial. Just for the hell of it, I'll write t to the 6 over 8 factorial. You see the pattern here, dt. Now that's actually, you can see that it's not an improper integral. I forgot to write this in my book. I just noticed this. This actually shows that the limit is a half. Right? Forget the integral. I claimed that that previous limit when t goes to 0 is a half. Plug t equals 0 and all these terms go away and you get 1 over 2 factorial, which is a half. Anyway, let's do the integration. Pull a bit of a rabbit out of the hat and assume that I can integrate this term by term. So I get t over 2 factorial minus t cubed over 3 times 4 factorial plus t to the 5 over 5 times 6 factorial minus t to the 7 over 7 times 8 factorial, and so on. Evaluated between 0 and x. Plug in 0, of course, everything goes away. So just replace t by x, and you get the answer. X over 2 factorial minus x cubed over 3 plus 4 factorial plus x to the 5 over 5 times 6 factorial minus x to the 7 over 7 times 8 factorial, and so on. it's not clear that this is true for every x, but it turns out that it is. So what is true? What is this equation? This is, miraculously, an infinite series for this integral for any x. For any x, we have taken this rather improbable object here, this messy thing, and expressed it as a series. Beautiful. Amazing. So when I say, oh, you can't do this integral, actually, you can do it, but as a series. I dare you to find an antiderivative for this, by the way. Don't even bother. Now, you can't do it. But here's a series for it. Now, here's the deal. We want to estimate this quantity, the integral from 0 to 1. Well, just specialize, plug in x equals 1. And there is the exact answer. That's the exact answer, expressed as an infinite series that converges. In fact, it converges to this number. This is just some area under a curve. Just some particular curve with a particular area. It's a number. What is it? It's the series. But the problem does not say find an infinite series for it. It says find an approximation. And so what you need to do is you need to know how to chop off this series in order to be sure that what's left, as in everything after the chop-off point, is less than 1 over 3,000. Now, imagine this was not alternating. Imagine these are all positive terms. So that would say, to get to this integral, I need to take this, plus this, plus this, plus this, plus this, and eventually I take dainty steps, and whatever line I get very, very, very close to, that's the value of the integral, starting at 0, going up to this line. Now, the problem would be, if you chopped it off at any one point, there's still infinitely many terms building up, and it's kind of hard to work out how big they are. But this is an alternating series where the terms are getting smaller and smaller. So let's see. Suppose I start at 0, here's 0, and this is positive. Okay, one approximation would just be 1 over 2 factorial, which is a half. So the first approximation is a half. Where's the true value? Is it forward or is it behind me? Well, why is it behind me? Well, the next approximation would say take this a half, but subtract 1 over 3 times 4 factorial, which is 1 over 72. So I'm going to go back a little bit. That's a better approximation. The next one is forward, but not forward as much. So I've gone from an underestimate back to an overestimate. And now the next step will be backwards again, and I keep passing it. I keep going past it. In zooming it out a little bit, the true value would be, say, here, and I'm really going like this. Over, then back under it, then over, under. Over. So, the beauty of this is that at every time, the error is less than the next step. I don't need to worry about all the rest of them. If I've gone like this, how far away am I? I don't know, but I can be sure that whatever the next step is, I've gone even further away. So the error, the true back step I should have taken, is less than the one I just took. And the same with the next step, and so on. So with an alternating series, whose terms are monotonically decreasing, so the same thing as the alternating series test, with an alternating series, the absolute value of the error, well, just the error itself, is less than or equal to the absolute value of the next term after chop off. So in particular, we could use, let's get rid of the shrapnel here, we could use 1/2 with an error less than or equal to 1 over 3 times 4 factorial. That's the absolute value, which is, as I said, 1 over 72. Or we could use 1/2 minus 1 over 72 with an error less than or equal to 1 over 5 times 6 factorial, which is the next term. That is 1 over 5 times 720, which is equal to 1 over 3600, which is good enough. It's less than 1 over 3000. So the quantity, the estimate that I'm going to use is this one, 1/2 minus 1 over 72, which is 35 over 72. Okay, so actually, if I chop it off here, the error would be even smaller. 1 over 7 times a factorial would be the most. And so on. So the moral of the story is we have a different way of approximation. Write out the complete sort of object, and if it happens to be an alternating series, write it out, chop it off somewhere, look at the next term, take the absolute value, and if that's smaller than what you want, then it's good. If not, keep going until it is. Your approximation goes up to a certain point, and the error is the next term. It's very similar to the n plus 1, Rn is the n plus 1 type term. But you don't have to mess around with the C. Okay. That's all I have to say about approximation. So I've covered all of chapter 25. Now, we still have a little under 20 minutes, and I need to talk about power series. So, I want to move on to 26. What I'm going to do is spend the rest of today and a considerable chunk of next time on these power series problems. And then, what I'm going to do is complex numbers. So that's the topic for next week, but of necessity, this power series stuff is taking a little longer. The complex numbers will have to spill over, but the good news is that the last two topics, the last 2 weeks on differential equations, I can really just do in one, because it's not such a big topic after all. So that's the plan of attack for the rest of the semester, therefore the rest of the course. All right, so let's move on to chapter 26, which is how to solve problems involving power series, and more so than Taylor series. Okay, I would like to spend a little time telling you about radius of convergence. A power series about x equals a looks like this. The sum from n equals 0, although you don't have to start at 0, to infinity of an x minus a. Now, the sort of Taylor series we've been looking at are a special case where an is the nth derivative of some function f evaluated at a over n factorial. I've left out the power here. That's better. All right. So if you started with a function f, which you could differentiate, you get a Taylor series. But forget the function. Forget the f. Just look at a sort of general series like this, where I don't say anything about the an. They're just some coefficients. So this is like a polynomial of infinite degree. What I want to ask is, where does it converge? Forget what it converges to. Let's just try to ask, where does it converge? That's the first thing I want to look at. Well, we've seen some examples of power series. Here's an example. 1 over n factorial x to the n. Where does that converge? Well, it actually converges for all x. And we have shown earlier that it actually converges to e to the x. Whatever x you plug in, you get a convergence series, and the limit that what it converges to, that which it converges to, is e to the x, where x is plugged in with the value. So, on the other hand, here's another power series. Just x to the n. Have we seen that before? What is this? It's geometric series. Do you remember when that converges? It only converges when x is between -1 and 1, non-inclusive. Otherwise, it diverges. We discussed this last time, actually 2 times ago. And then it converges to 1 over 1 minus x. On the other hand, here's another series which I'll look at later, maybe later today, we'll see. N factorial x to the n. It turns out this only, so this is 1 plus 1 factorial x, which is just x, 2 factorial x squared, 3 factorial x cubed, and so on. If you plug in x equals 0, this surely is good. It's just 1. Right? X equals 0, everything goes away. But it turns out if you plug in any other value, it diverges. So the moral is converges only when x equals 0. Okay, so in general, what can we say about a power series and where it converges? an x minus a to the n. Well, let's try to draw a little number line here. What I want to do is I want to say, here's a number line, and I want to put a little check mark above every number if it converges at that number x, and I want to put a cross if it diverges. Of course, I won't be able to fit all these crosses and checks in there, but I'll try to give an example of what's going on. One thing I can say for sure is that when I plug in a, the center of the power series, everything vanishes. Everything goes away except the first term, so it definitely converges at a. But what about any other number? Well, it depends on the series, of course, but maybe you think it could be possible to have a bunch of, goods and bads and converging. Why couldn't it be some sort of hodgepodge where, this means it converges around here, diverge. Why couldn't it be like that? Well, it turns out it can't. There are 3 possibilities of where a power series converges, and you should be familiar with them, even though every problem we ever do, the thing will just jump out. But it's good to not be surprised. So it turns out there's 3 possibilities. So let's take a little bit of time to look at them. 3 possibilities. Possibility 1. The series converges for x no more than a plus r or less than a minus r. I'll just do this less than for the moment. And diverges when x is bigger than a plus r or x is less than a minus r. Well, when I write it like that, it's almost meaningless. Here's the way to see it. Draw the number line. Here's a, that's the center, and we know it's always good there. There is some number r where if you go r that way or r this way, you are good inside here. So the check means that the series converges for those values of x if you were to plug them in. And it diverges outside. Now, a couple of comments. A good way to rewrite this inequality, another way of saying this is that the distance between x and a is less than r. On the number line, x minus a, absolute value, is the distance from x to a. And in this case, x minus a greater than r. So that's one comment. You can write those inequalities as one absolute value inequality. Another comment is that at the endpoints, x equals a plus or minus r, you cannot tell. Anything could happen. and you have to check separately. So maybe here I put a question mark for that one particular point and another question mark here. Now we've seen this case for the geometric series, that middle case above. For the geometric series, I'll just pull this down for a second. The center is at 0, and it converges between -1 and 1, but diverges actually at 1 and at -1 and everywhere else. So look at that picture, and that's a special case of this more general picture. There we go. The number r is called the radius of convergence. And the reason it's a radius, imagine taking your compass, sticking it on the center A, and mark off this arc here, boom, and boom. And when we do complex numbers, actually you get a full circle, because instead of a line, you have a plane, but that's not until a little later. So then it looks like a circle rather than just a little interval, but you can still imagine the compass. So r is the radius of convergence. And this is like this is a possibility of what can happen. Okay, so be familiar with it. Luckily, the other two possibilities are much simpler. Possibility 2, the series could converge. Oh, actually, before I go here, I want to say that not only does it converges absolutely. We talked about that last time. So it converges absolutely. And it diverges where there's a cross, as in outside, and at the endpoints, it could actually, at those 2 points where I put question marks over here, it could converge conditionally, or converge absolutely, or diverge. There's 3 possibilities. And the other endpoint could do the same, and they're more or less independent. You have to check. Okay, so the second possibility is that the series converges absolutely for all x. So that's very simple. What do you think the radius of convergence should be here? Infinity. You take your compass, you make it infinite, you get everything. And the third possibility, and an example of this is the e to the x series that we looked at. Maybe we can zoom up to the first formula up there, 1 over n factorial x to the n. That converges for all x. So that's an example of this. Anyway, so the third possibility is that the series converges absolutely at x equals a and diverges for all other x. So this is the grim situation where you get a solitary check mark and everything else sucks. And of course here, r equals 0. Radius of convergence is 0. So you can never actually avoid convergence at one point, A. You may get just that point. You may get every point, or you may get some in between. Those are the only possibilities. Now, how do you know which one? The answer is you use the ratio test. So I'm not going to have too much time to do problems. I'll probably have time to do one. And then maybe I'll do some more at the beginning of next time. So I'll just do one problem. Although I'll give a variation of it as well, so it'll be 2 problems for the price of 1. Okay, so here is a typical type of problem. I give you a power series, and I ask, what is the radius of convergence? Or maybe I even ask, where exactly does it converge? And if it converges, is it absolute, or is it conditional, etc.? So check out this problem. Let's do this one. Okay, so here is a bizarre series. It happens to be a power series, an x minus a to the n. So here the a is 7. It might be worth just noticing that the center is 7. So my question, which I'm not writing down, is this. What is the radius of convergence of this power series? Also, I would like to know, where does it converge? And I'd like to know, is the convergence absolute or conditional? Those are all the things I'd like to know. And I have 5 minutes to find out. So, my main tool in all of these problems is going to be the ratio test, again. Occasionally the root test, but almost all of the time, use the ratio test. And we will see which one of these cases it is, but we will not be surprised when we get one of the cases from the previous board. So let's use the ratio test to investigate this series. So the limit, as n goes to infinity, of, I don't know what to call it, maybe I'll call it capital AN plus 1 over AN, and here it's vital that you have the absolute values, is, all I do is copy the exact term down the bottom, under this huge fraction bar. I get minus 2 to the n over root n, x minus 7 to the n, and on the top I increment n. I get minus 2 to the n plus 1 over root n plus 1, x minus 7 to the n plus 1. Notice that it's n that I'm increasing, not x. X doesn't get touched. I'm leaving x as it is. Okay, so let's group. You get minus 2 to the n plus 1 over minus 2 to the n. You get root n over root n plus 1, which does not need absolute values. And you get x minus 7 to the n plus 1 over x minus 7 to the n. There's a bit of cancellation we can do. This just becomes minus 2. And this just becomes x minus 7. So the absolute value of minus 2 is 2. The square root I can write as n over n plus 1. And here I have the absolute value of x minus 7. Okay, this is just the ratio test. I just got this extra little term floating around that I wouldn't have had otherwise. Now, what happens as n goes to infinity? 2 stays as 2. Oh, hell, I wrote an x there. Man. I was just trying to trick you. Okay, as n goes to infinity, what happens to n over n plus 1? Goes to 1. Square root goes to 1, 2. So this goes to 2 times 1 times absolute value of x minus 7, which is 2x minus 7. And that is the limit L from the ratio test. What is important about this? It has to be less than 1 for convergence. What if it's bigger than 1? Divergence. What if it's equal to 1? You can't tell. So let's see. If 2x minus 7 in absolute value is less than 1, series converges absolutely. But if it's greater than 1, it diverges. Now, let's play around with this for a little bit. Maybe I should have left more space here. i.e., x minus 7 is less than a half. I just divided by 2. And in this case, x minus 7 greater than a half, it diverges. Let's draw a picture of it. Here's 7, center of our series. A half takes us to 7.5. 6.5 on the other side. And what we know is that between 6.5 and 7.5, it converges absolutely. And outside 7.5, or minus 6.5, outside that interval, it diverges. So what's the radius of convergence? No, 7 is the center. 1/2 is the width of this, or the diameter is 1, but the radius is a half. and it's just this number here. So radius of convergence is 1/2, and we know that the series diverges to the right of 7.5 or to the left of 6.5 and converges absolutely in between. Converges absolutely 6.5 less than x less than 7.5. And it diverges x greater than 7.5 or x less than 6.5. That is the one thing we don't know. So I've almost answered the question. I've brought down infinitely many points that we didn't know about down to just 2 points that we don't know about. But we still need to check them. So let's check them individually. Unfortunately, the ratio test will not work because this is where it equals 1. The ratio equals 1. So let's check x equals, say, 6.5. So we've got to go back to our original series, which is sitting right at the top of the board there, and plug in x equals 6.5. Let's do it. Series is sum from n equals 1 to infinity minus 2 to the n over root n times 6.5 minus 7 to the n. So I've plugged in 6.5. What is 6.5 minus 7? Negative 1/2. So this is negative 1/2. And another way of writing this is minus 2 to the n times minus 1/2 to the n over root n. Well, a to the n, b to the n is just ab to the n. So you can multiply the minus 1/2 and the minus 2 and get 1. So this is just n equals 1 to infinity, 1 over root n. Does that converge or diverge? That's just a regular old series. Diverges by the p-test. So we have discovered that this endpoint here diverges. However, what happens at x equals 7.5? We check this and then we go home. Series is minus 2 to the n over root n times 7.5 minus 7 to the n. 7.5 minus 7 is 1/2. So you get the sum from n equals 1 to infinity of minus 2 to the n times 1/2 to the n over root n. And now, minus 2 times 1/2 is minus 1. So you get the sum from n equals 1 to infinity minus 1 to the n over root n. What sort of series is this? Alternating. But remember, before you use the alternating series test, check the absolute convergence test first. I talked about this last time. Well, actually, the absolute version of this series is just there, which diverges. So it's not absolutely convergent. However, I'm going to leave it to you to use the alternating series test. Remember, you have to check alternating, that the terms are decreasing monotonically, or, I'll just say decreasing if you ignore the alternation, and also that the limit is 0. And you can show that, therefore, that converges conditionally by the alternating series test. There's a little bit of details for you to fill in there. But basically, the end result is that you do have convergence there, but only conditional. So it's worth adding this to the summary here, that it converges, it actually diverges at x equals 6.5, but it converges conditionally x equals 7.5. So there is the complete answer to the problem. Anyway, next time we'll do another example or two. See you then.